explaining the laboratory activity number 12, which is the media processing. The first line, import of PSNP, is for numerical operations, arrays, FFT, and noise generation. Then the second line, the import matplotlib, is for plotting waves, spectra, and images. And then the librosa and the librosa display naman is for audio loading, visualization, STFT, and spectrogram display. This SciPy signal import butter and the L filter naman are for designing and applying Butterworth IIR filters for audio. The CV2 is for image processing such as reading images, filtering, blurring, and denoising. And then the last but not the least, the IPython is for playing the audio directly in Jupyter notebooks. Then let's now dug into part A, which is the audio signal processing. File path librosa YSR librosa.load. So it loads a sample trumpet audio file where Y is the audio samples, amplitudes versus time, the SR is the sampling rate, and the SR equals none is to preserve the original sampling rate. Then this line naman, the length Y over SR, computes audio duration in seconds. Then to plot the waveform, this line is added. The librosa.display wave show, it displays the time domain waveform of the audio signal. So then these two lines, the D librosa and the SBB librosa, the first line converts the signal from time domain to time frequency domain. And the other one is to convert magnitude to decibel scale, which makes the frequency content visually interpretable. In this slide, the librosa.display, it shows how frequencies change over time on a logarithmic frequency scale. Then you can see the depth, buff, butter, low pass filter. The function of this line is to define a function to remove high frequency noise. At sa baba naman, you can see the Nyquist frequency, 0.5 times Fs. It is the Nyquist frequency which is the maximum usable frequency. Then sa baba naman niya is the normal cutoff or the cutoff over Nyquist frequency. It normalizes cutoff frequency for digital filter design. And these three, the BA equals butter. It designs a low-pass Butterworth IR filter, and the Y filter naman applies the IIR filter using a difference equation. Then these two lines, the cutoff and the Y filter, this removes frequencies above 1000 Hz from the audio. Then you can see here the display audio Y uh, this line. You can see here, it plays the original audio, and then the display audio Y filtered, which equals SR, displays the filtered audio to hear the effect. Let's now go to part B, which is the image signal processing. You can see the IMG, this line, you can see here, this loads the image in grayscale, which is a single intensity channel. This line, the PLT.HIST image ravel, it displays the distribution of pixel intensities. And then the next is the F equals NP.FTT, FFT.FFT2. So this transforms the image from spatial domain to the frequency domain. And then this next line, the F shift, moves the low frequencies to the center of the spectrum. Then the magnitude spectrum naman equals 20 times np.log. It log scale the magnitude spectrum for visualization. Then this blurred equals CV2 dot Gaussian blur. This applies a spatial domain low pass filter which smoothens the image by removing high frequency details. So as you can see here, nag-add tayo ng noise. It generates random Gaussian noise. It adds noise to the image, and the NP clip naman ensures valid pixel range. Then to the noise using the median filter, the noise equals CV2.median blur. It removes noise using a median filter effective for impulse noise. And then you can see here, it prints the it computes the signal, the first line, original signal energy and p.sum. It computes signal energy. The second line, which is this, the 1 minus np.sum, it estimates high frequency attenuation due to filtering. And then this line naman, the original mean intensity, the mean brightness of the image. And the NPSTT naman is measures the noise strength. Now, let us now see the code, the output of this code. Now, we can see now the audio waveform, which is the trumpet sample. Here's the amplitude and the time. This is the spectrogram in dB scale, decibel scale. In hertz, this is the intensity in decibel, and this is the time. You can see here. And now, this is the original audio signal, the first 4,000 samples. You can see. And then, the low-pass filtered audio signal. Mas gumanda siya. And now, you can see, here is the original image. 512 times 512 pixels. Malinaw siya. Here is the image histogram. You can see frequency and the pixel intensity. Original signal compared to the magnitude spectrum, the FFT. Luminaw siya. Yan. Original signal, lumabog siya, blurred image, 9 by 9, Gaussian kernel. And then, ito pa. Original signal compared to the noisy image, Gaussian noise equals 25, and the denoised image, 5 by 5 median filter. Thank you so much.